In this video I'm going to use some relatively simple data in order to illustrate how a line shape can be created from data and then used in a peak model to fit these data. I'm also going to create a line shape that has the characteristics of a Shirley background that is based on the photoemission peak. And the idea is to estimate the energy offset between the photoemission peak and the point at which inelastic scattering begins to create a rise in the background that is associated with this particular photoemission peak. The background beneath the peak itself derives from inelastic scattering due to photoemission with higher kinetic energy, and in this particular case the background is relatively flat beneath the peak, so we can see the point at which inelastic scattering is starting to contribute to the background signal that is due to this photoemission peak itself. To create a line shape from data, the first job is to create a background that is appropriate for the peak in question. So I've brought up the quantification parameters dialog window, and on the regions property page the background over an energy interval can be created. So I press create, it creates a region with a set of parameters defining the region, and one of these parameters includes the background type. And I'm going to create a minimum limits background, and I would like the background to show me the points over which the peak exists. So here I can see the background touches the data at this point and it's defined by this end. So if I adjust the limits to the background, I end up with something that is a reasonable approximation to what inelastic scattering from higher kinetic energy photoemission looks like beneath this peak. So now all I need to do is use the spectrum processing dialog window, and on the test data property page the option background subtract, and this provides me with a peak that is now background subtracted, and over this entire energy interval where the data previously existed, the only signal above this background is within the region itself. The data we see in this active tile corresponds to this VAMAS block, and within this VAMAS block there is the process data we see here, and there's also raw data. We need to preserve the process data so that it's available if we want to use this as a line shape. So to preserve the process data we need to copy the data using the process data only tick box active, and this will cause, when I press OK, the creation of a new VAMAS block within this file, and the new VAMAS block contains only the process data. So if I go back to the original VAMAS block, the one that had processed and raw data, I can go to processing history on the spectrum processing dialog window and undo the background subtraction. So there's the data in its original state. It also has the background still active, which we can see the region if we display the region as a different color, and the new VAMAS block contains only the process data, no region, no processing history, simply the data itself is now the processed form of the previous VAMAS block. And this is the VAMAS block we can turn into a line shape. A VAMAS block can be used as a line shape if we change the block ID string so that it has a prefix which indicates that we are intending these data to represent a line shape. So what I will do is, using the edit VAMAS fields, alter the block ID string and give a prefix of %, less than, greater than. Then any string I like may follow that. I'm going to call it silicon2p, and when I press return we'll see this name here update with the name that I've entered in the block ID. So now we have a VAMAS block in a state where we could use it in a peak model as a line shape. Now that a VAMAS block has been created to represent a line shape, it can be used to construct a peak model. and we'll construct the peak model on the data from which the line shape was created. So it's a very simple peak model. All we require is that this line shape with this background should fit these data. So what I will do is copy from the text field on the quantification parameters dialog window the string that represents the line shape from data. Now if I display the data itself that I wish to fit, it already has the background through a region, and if I create a component, the component is entered with a default line shape, but I can modify this line shape in the line shape field by entering the string that defines the VAMAS block that will be used to create the line shape from data. So when I press return, then the dialog window asks whether I want to fix the full width half maximum, and the answer is yes, predominantly when this dialog is offered. And when the line shape is defined and we fit to data and show the residual, then we see a residual that is 10 to the minus 12. So the fit of the line shape from data to these data with the background that was used to create the line shape is fitting with the type of precision that you would expect. In other words, almost perfect. So that is an example of how a simple peak model can be created from a line shape. But the most important thing to appreciate about a line shape from data is that the string entered into the line shape field must match a VAMAS block within this file, or it must match the string that was used in another file that has previously made use of a line shape with the same name that has been entered into a list of available line shapes. So when I created this component and entered the line shape for the first time, this particular line shape was entered into the list of possible line shapes. We can see this list if I click where it says line shapes, and you can see the list of line shapes that are currently available, and at the end there's the line shape that has been created from data. So this represents a list of cached line shapes that are now available for use in CasaXPS, and it is added to once a line shape has been used. So having created a line shape from data, I would now like to make use of that line shape to look at the way the background rises at lower kinetic energy from the peak itself. The idea will be to create a component that has a shape that represents the sigmoid type shape that we see in response in the background to this photoemission peak. And I'll do this by taking a copy of the line shape from data and adding it to the peak model, and then introducing a prefix which is SB, and initially it'll be set to 0 within brackets, then followed by the name that was used for the line shape. And when I press return, I end up with a component that is not visible at the moment, but what I need to do is alter some of these parameters, such as the range of areas that are available for the area parameter itself, and then we'll increase this by a factor so we can see this clearly. So here is the type of shape that you might expect from a Shirley background applied to these data. There is a point at which the background starts to rise up, and this is the point in the data where I'd like the Shirley based component line shape to fit the data and give us a measure of what type of offset in energy there is between this rise in the background and the peak itself. The Shirley component has been created from the original component, which is the line shape from data. Now I had to adjust the area constraint to allow the range of areas necessary to fit a Shirley type background component to data. I also need to account for the fact that the data that I wish to fit is outside of the original region. So I need to increase the range for the position parameter. I'll just make that say plus or minus 20, whatever the current value is, and that will give me enough of an energy interval over which the position can move that will allow this component to be positioned outside of the original region. So when I go to the regions property page and I extend the region so that it includes this sigmoid type shape, it's possible to move the Shirley component and slide it so that it is now outside of the original region, which it would otherwise not have been able to do if I hadn't changed the position constraints. We can now fit these data by pressing the Fit Components button, with these two components, one representing the photo emission peak, the other a rise in the background. So I press Fit Components and we end up with some type of fit to these data. The idea originally was to work out what the offset is between the photo emission peak and the rise in the background, and this can be done by using the position constraints and using a relational constraint between B and A. If I type A into the position constraint in B and press return, then it calculates the offset. So we get to see here what the offset is between the photo emission peak and the rise in the background. It's about 10 eV. It's always a good idea to use the correct names for these photo emission lines, so we'll change that to silicon 2p, which is what the photo emission peak is, and this is photo emission background signal, and there really isn't any RSF that corresponds to that, so we'll set that to 0. And then we might add a table that includes maybe the position offset so we can see the position that we've just calculated. And there's the offset 9.9.